Hey guys, welcome to the last video on the alkene reaction pathways you're required for your exam 1. And so this one is going to be covering what's called the concerted pathway. So this is probably the easier of all of them simply because they kind of happen all at once. There's no real mechanism that you have to know for these, which is great. But before I get into that, I just want to quickly talk about one of the reactions I showed you before, and in general about the three-membered ring intermediate reactions. And this rule applies to these too. There are no rearrangements for these reactions, only the carbocation reactions. So I'm going to give you guys a quick example that was given on one of my exams last year. I think it was exam 2, because we did alkene addition in exam 2. So they gave us this compound, and they gave us a oxymercuration. So it was written like this. And so they gave us this reaction, and then they asked us simply, what's the product, right? And so a lot of people, because they see this four-member ring, will assume that it's going to be a ring expansion, right? It's perfectly set up to look like a ring expansion. And if we gave a reaction such as HCl instead, you will 100% get a ring expansion. The only problem is the HCl reaction goes through carbocation. This reaction over here, no carbocation, therefore no shift. And so if we remember, if you want to take a second and try to figure out the answer yourself, please go ahead. And so, because I'm going to do it right now. And so if we remember the reaction from the previous video, I will not go through the whole mechanism. The shorthand way of doing it is knowing that the OH from H2O, or if it was an ROH group, it would be the OR group, adds to the more substituted carbon of the double bond. No shifting, none of that. And so all we have to do is redraw our structure, but the OH is boom right there. And then we're done. A lot of people ended up trying to go through something like this. They had a carbocation here, the ring opened, and you'd get a 5-membered ring. Okay, you should not be getting a 5-membered ring in this. There is no shifting. A ring expansion counts as a shift. Okay, and so do hydrides and alkyl shifts. And so I just wanted to get that quickly just out of the way, just to mention that. And the same applies to the reactions I want to show you in this video. And so our first reaction, it's going to be somewhat similar to the oxymercuration reaction I just showed you and in the last video. It's called a hydroboration reaction. So I'm going to set up an alkene similar to what I showed you in the previous video because I want you guys to see the difference between the oxymercuration and the hydroboration. And again, this reaction is also in multiple steps. And so you must number them. Don't forget the numbering. If you're writing these reactions on your index card, which I suggest you do, make sure you include the numbering. And so it's going to react with BH3, step 1. Step 2, it's going to be H2O2, hydrogen peroxide, and OH minus. It could be written as NaOH or KOH. Don't get tripped up by that, it doesn't matter. And so the great thing about this reaction is you don't need to know the mechanism for it, okay? And so I'm just going to kind of skip ahead to show you the answer for what the product, I guess, for what this reaction would look like, rather than go through a mechanism that you do not need to know. All right, and so, like I said, this reaction is going to be similar to the oxymercuration reaction we saw previously. Okay, and so what it's going to do is it's going to add an OH, but it's not going to add it to the more substituted carbon like the oxymercuration did. It's going to do it the opposite way and add it to the less substituted carbon. And so actually what I'm going to do is I'm going to label where everything is coming from, okay? And so I'm going to color our H2O2 in purple, okay? And our BD3, I'm going to color it red. Right, sorry, not BD3, BH3, sorry about that. Okay, and so the OH that's being added comes from this hydrogen peroxide, okay? And so what it does is it adds an OD, sorry, oh my god, I'm thinking about the deuterium, sorry about that, an OH on the less substituted carbon. The H from the BH3 adds to the more substituted carbon, so right there. And so if we talk about this in the context of Markovnikov's rule, the OH right here, because it adds to the less substituted carbon, is anti-Markovnikov, and I'm just going to write as Mark, and the H adds Markovnikov, okay? And so let's talk about it in the context of the deuterium labeling, just because I was stuck on that, and it's also a good way of knowing where everything is adding. And I'm going to do it with both the oxymercuration and the hydroboration so you see the difference. So let's start out. Here's our alkene, and we're going to have one direction is going to be B. Oh, let's change the coloring up. We're going to have BD3, and our step 2 is going to be H2O2 OH minus. That's our hydroboration. And our alternate one from the previous video is going to be the oxymercuration. So HgOAC2, our H2O. Step 2 is going to be our D3, NABD4, and that's going to be D2O. And this is going to be D2O2. And NaOH. And so the hydroboration adds to the least substituted carbon. So when we draw our product, we're going to add an OD to the less substituted carbon. So remember, this OD comes from the D2O2. Okay, it doesn't come from BD3, it doesn't come from OH minus. The deuterium from BD3 adds to the more substituted carbon. Okay, and so this is going to be the opposite of the oxymercuration. So remember, we're adding the OD now to the more substituted carbon, and it comes from the water. And I should have changed this color over here. Let's change it to red. So our OD comes from the water, and it's on the more substituted. And on the less substituted, we get the deuterium from NABD4. Okay, so that's the difference between these reactions. And so that's a hydroboration, and it follows a concerted pathway, which means it's all at once almost. And there are no shifts for this reaction either. Just like in the last videos, none of the reactions in this pathway undergo shifting anyway, all right? And so we only have one more reaction to go through, and it's probably going to be the easiest one to go through. And so I'll draw this alkane, and it's called a hydrogenation reaction. It's going to be H2 over a metal catalyst. Usually you'll see either written PD for palladium or PDC. I just always wrote PDC on my test. And so what this reaction does is it adds hydrogens across double bonds. And so let's color code the hydrogen. Let's write H2, and it'll add them across alkenes to make them alkanes. And so we already had one hydrogen here. We had two hydrogens here. Now we're going to have our original hydrogens. But we have a hydrogen here now that's added and a hydrogen here. And so it turned it into an alkane. And now the cool thing about this is it can work across multiple double bonds. So if I had this really long structure, here's some branching, double bond, double bond, double bond, and I went through H2PDC, our answer would look like this. All the double bonds gone. All right, but one quick thing to watch out for are benzene rings. This reaction does not work on a benzene ring. So if I had this structure here, a benzene ring with some sort of chain coming off of it, and that double bond part of the chain, the benzene ring is too stable. H2PDC does not work on it, but the alkene part of that chain is fine. So it will undergo the hydrogenation reaction. All right. And also, these are the thing about your guys' exam is that you're not learning stereochemistry with alkene additions, and so you don't have to worry about the way that some of these add. You'll see that some of these add to like, oh, they can create wedges and dashes and all that sort of thing. We do not worry about that for you. You're not going to have to worry about that for your test. And so you only have to know essentially what has been shown in the videos and anything in lecture. If when you guys get through the lectures, if I see that there's something that you learned in there but I didn't show here, I will definitely add that, and I'll make another video about it. And so, yeah, and so that covers all the reactions you'll need to know in terms of alkenes for this test, as far as I know. There are some you'll be covering after this test as well that you're not getting to for exam 1. But yeah, and so if anything in this video didn't make sense, please feel free to email me, go to the CLC for TA office hours, and I hope this video helped you guys.